Okay, so so I'm trying something new yet again. Um, so we're going to, whoops. Yeah, so bear with me while I try to work out all the kinks here. But I finally got a doc cam and I have a webcam, and so I can record lectures this way, which I think hopefully works out a little better. Hopefully the sound is a little better, and so forth. Uh, so let's look at 9.3, which is about estimating the population standard deviation. Okay, so in 9.1 we estimated proportion p. In 9.2 we estimated the mean mu. And so now we're going to estimate the variance, right? We're going to estimate the variance sigma squared, and hence the standard deviation sigma. We were able to build confidence intervals for the proportion and the mean because our work in chapter 8 showed us that the sample proportion and the sample mean had approximately normal distributions under the right conditions. We haven't looked at the sampling distribution of the sample variance as squared, right? So we don't know what that distribution looks like, but so we could go through a similar process as we did back in chapter 8 for x bar or for p hat. We're not going to. We're just going to pretend that we did, okay? So pretending that we've done that, what we would find out is that the ratio of the sample standard deviation, or sorry, the ratio of the sample variance to the population variance follows what's called a chi-square distribution, okay, with n minus 1 degrees of freedom. And here degrees of freedom are the same as they were for students' t distribution, okay? So it's you have 1 less than your sample size. That's how many degrees of freedom you have. Now this distribution, the chi-square distribution, is an interesting one. Unlike the t distribution and the normal distribution, this is not a symmetric distribution. And the shape of it changes pretty drastically depending on the degrees of freedom, right? Depending on how many degrees of freedom you have. So here's a chart. And this comes from your notes, right? But this blue one shows you what the chi-square distribution looks like when you have 2 degrees of freedom. The red dotted line is when you have 5 degrees of freedom. This is with 10 degrees of freedom, with 15 degrees of freedom, and then finally in purple when you have 30 degrees of freedom. By the time you get to 30 degrees of freedom, then it starts to look a little bit more symmetric and bell-shaped and stuff like that. It's still not perfectly symmetric though. Anyway, so it's really kind of a pretty interesting distribution, and we'll take a look at some of these things in StatCrunch here together in a second. Okay, so to construct our confidence intervals, we need to use a StatCrunch calculator to find the critical values. Since this distribution, right, since the ratio of the sample variance to the population variance follows a chi-square distribution, we're going to use the chi-square calculator to find the critical values. Okay, so our critical values are going to be chi-square critical values. By the way, I should mention this is the Greek letter chi, right? So it's kind of like an X. We spell it C-H-I, so so a lot of you are going to be tempted to call it chi, right? So you're going to call it the chi-square calculator, but it's chi, right? So it's the chi-square calculator. Anyway, so we use chi squared sub alpha to denote the critical chi-square value such that the area to the right of chi squared sub alpha is alpha. Which is a confusing way to say that we're going to be doing the same thing here as we did previously for finding critical values using the normal distribution or the t distribution. So just to give you an example, this one says find chi squared sub 0.05 assuming 18 degrees of freedom, okay? So to do that, we're going to use the chi-square calculator. Let's take a look at it in StatCrunch. So I have StatCrunch pulled up here. Okay, So to use the chi-square calculator in StatCrunch, you're going to go to Stat, Calculators, and chi-square. Right, and so you can see, you know, here is this kind of funky looking distribution. In this example, we were asked to assume 18 degrees of freedom. So I'm going to use 18 degrees of freedom. And we're looking for an area to the right. Okay, we want that area to be 0.05. Okay, so there is that chi-squared critical value. Okay, so rounding that, we'd say 28.87. Okay, so it's approximately 28.87. Okay. So I'm going to say, here, let me make this full screen so it's a little bigger anyway. So we would say, well, we went to Stat, Calculators, chi-squared. And, well, it was actually written out, wasn't it? And then we found the critical value, right? Chi-squared sub 0.05 was approximately, oh, what did I say? Here, I can do this. And this is something that I couldn't even do in class, but I can split the screen this way and you can see both sides of the screen. It's really a pretty nice system, I think. Anyway, so this is about 28.87. Okay, you can probably hear my kids running around. I'm in my son's room, by the way. And you can, oh, here is, Maggie. That's my daughter, Gwen. I don't know where Maggie is. Okay. I should have locked the door. Anyway, I'm in my son's room because this is the only place I can barricade myself away from everyone else. And as you can see, like it's missing some molding and stuff. We're in the middle of doing some renovations. Anyway, continuing on. Okay, so this is how we find critical values. All right. Maybe I'll make this full screen again until we actually need StatCrunch. Okay. So if we wanted to compute these confidence intervals, here's how we're going to do it, right? So because the chi-square distribution is not symmetric, we actually have to compute two different critical values, one for our lower bound of our confidence interval and one for the upper bound of our confidence interval, okay? And so consequently, we have two slightly different formulas for the lower bound and for the upper bound in this case. But these are the formulas, and actually they're not terribly complicated. You just need the sample variance, the sample size, and the critical value, right? And you plug in the numbers. Again, you can take a look at the textbook information of this formula, okay? But this is what's going to do the trick, okay? Now, these bounds are going to give you a confidence interval for sigma, the standard deviation. Then you need to take the square root of these lower and upper bounds, okay? So I'll show you an example of this in a second. Okay, let's see, what am I saying here? So in order to get these critical values, these chi-square critical values, we have to use StatCrunch to do it. Since we're going to have to use StatCrunch to get the critical values anyway, we might as well just let StatCrunch do all of the calculations for us. So I'm actually not even going to give you an example where I use these formulas. We're just going to let StatCrunch do this. Okay, to do a confidence interval or a variance, you enter the raw data if you have any, and then you're going to go to Stat, Variance, Stats, One Sample. Okay, and then you'll choose either with data or with summary, depending on what you have. Whether you have the raw data or just a summary of the data. So let's take a look at some examples, right? So this one says, a simple random sample of size 10 is drawn from a population that is known to be normally distributed. The sample variance, S squared, is determined to be 19.8. Find a 95% confidence interval for sigma squared and sigma. Okay, you know, I failed to mention this on the previous page, but it's good that they're telling us, right? It's good that, so they're saying a sample of, we have a simple random sample size 10. It's drawn from a population that's normally distributed. We have to have that condition, right? The underlying population has to be normally distributed. Otherwise, we can't construct the interval, okay? And it doesn't even matter how large the sample size is. We have to, in order to construct this confidence interval, we have to have a population that's normally distributed. Okay. So let's construct this interval. In StatCrunch, we're going to go to Stat, Variance Stats, one sample. And in this case, we don't have raw data, we have a summary. So we're going to say with summary. Okay. Once we do all of that, StatCrunch is going to prompt us for, it's going to prompt us for the sample size. Okay. In this case, we're told we have a simple random sample of size 10. And it's going to prompt us for the sample variance. Okay. In this case, we're told the sample variance is 19.8. And then, of course, it's also going to prompt us for confidence level. In this case, we want a 95% confidence level. Okay, so let's go to StatCrunch and enter all that information and see what we get. Here we go. Okay. So we go to Stat, Variance Stats, one sample with summary. Our sample variance we said was 19.8. Sample size we said was 10. We want a 95% confidence interval. And notice it's a confidence interval for sigma squared, right? For the variance. Okay. Anyway, hit compute. Gives us all kinds of good information. This is what we're looking for. Our lower limit and our upper limit. Our lower bound and our upper bound. So this is the lower bound for our confidence interval and the upper bound for it. Okay. So we can write that down. Okay, so I'm going to say, so my confidence interval for the variance, right, for sigma squared is it's about 9.37 to 65.99. Okay. So in other words, we know that the sample variance was 19.8. There's no ambiguity there, right? We know for a fact that the sample variance was 19.8. But based on having a sample variance of 19.8, what can we say about the population variance? Well, if the sample variance was 19.8, we can be 95% certain that the population variance is somewhere between 9.37 and 65.99. Okay, that's the meaning of what we just did. Okay, so if the sample variance is 19.8, then we are 95% certain that the population variance is somewhere between 9.37 and 65.99. This is a confidence interval for the variance. We were asked to construct a confidence interval for variance, but also for the standard deviation. Okay, so to find the confidence interval for the standard deviation, we just take the square root of the upper and lower bounds here. So our confidence interval for the population standard deviation would be square root of 9.37, square root 65.99. Let me make this full screen again. Okay, and let's see about how much that is. Actually, you know what? Let me do this. A better thing to do here would be to use these full numbers, right, from StatCrunch. I'm just going to find these entire, I'm just going to plug in those entire numbers. If you plug in 9.37, you've already done some rounding here. You're going to get some rounding errors, okay? So let me plug in this whole number instead. So I'm going to say square root of 9.367722. If you're using a calculator on your computer, actually, you could just copy and paste it, which is even better. That way you're sure you're not making any mistakes. But I get 3.06 square root of 65.99048 is 8.12. If I had just plugged in these numbers, I wonder what I would have gotten. Square root of 9.37, 3.06 again, if I round to 2 decimal places. So I guess you wouldn't have had too much of an error there. And if I just plugged in square root 65.99, again, to 2 decimal places, it's the same number, 8.12. So maybe there's not so much of a rounding error issue. But if you're going through the homework and you're looking at the back of the book trying to get the answer that they have, and you're off, you know, your answer is like 2.57 and the book's saying that it should be 2.55, you know, this might be part of the issue, right? Anyway, but that's my confidence interval for sigma. That was my confidence interval for sigma squared. Okay, so again, the interpretation of this is that we are 95% certain that the true population standard deviation is somewhere between 3.06 and 8.12. Okay, so that's that one. Let me give you one more example. Okay, so it says, one way to measure the risk of a stock is through the standard deviation rate of return of the stock. The following data represent the weekly rate of return in percent of Microsoft for 15 randomly selected weeks. Compute the 90% confidence interval for the risk of Microsoft stock. Okay, so we have this data here. We want a 90% confidence interval for the risk of Microsoft stock. Well, what's the risk? The risk is the standard deviation of the rate of return, right? These are the rates of return. So we want to figure out the standard deviation, right? We want to come up with a 90% confidence interval for the standard deviation. Okay, so let's do that. We don't have any summary statistics here. We have the raw data. So we're going to have to enter this data into StatCrunch. So let me do that. You could probably fast forward, although you should do this too. You should do this along with me. 5.4, 9.63, negative 2.38, 3.54, negative 8.76, 2.12, negative 1.95, 0.27, 0.15, 5.84. I'm going to stop talking. Okay, so I've got them all in there. Let me just double check that I did them correctly. Okay. So, all right, so to construct this interval now, I'm going to go to stat, variance stats, one sample with data. I have the raw data, right? So I'm going to say with data. My data is stored here in the variable one column. I want a confidence interval. I wanted the confidence interval to be a 90% confidence interval, right? So I'm going to change this to 90%. Maybe I should write down where I'm going, right? So I'm going to stat, variance stats, one sample with data this time. And the only thing I had to feed it was the confidence level that I wanted, right? So I wanted a 90% confidence level. Okay, let's see what we get. Okay, there's our confidence interval right there. Okay, so, but that's our confidence interval for the variance, sigma squared, right? Okay, that's not exactly what we wanted. We wanted a confidence interval for the risk of the stock, right? So for the risk of Microsoft stock. And the risk of the Microsoft stock is given by the standard deviation, right? The standard deviation rate of return. So we need to take the square root here. See what we get. So I'm going to do square root of 13.043052. That's about 3.61. And then I'm going to do square root of 47.015569. And that's about 6.86. Okay, so there's our confidence interval. Okay, so we can be 90% certain that the risk of Microsoft stock is somewhere between 3.61 and 6.86. And again, right, if you're thinking about this, it should make some sense. The standard deviation measures how spread out data is. If the data is really spread out, if there's a lot of volatility in the stock, then that would mean it's more risky, right? Well, if there's more volatility, if there's more variation, then the standard deviation is going to be higher, right? So on the low end, we can expect, 3.61 as our measure of, volatility or risk. On the upper end, we would expect 6.86, right, as the volatility there. I bet if you compared that with other stocks, that's probably not a very risky stock, but I could be wrong. I've never traded on the stock market, so I really have no idea. Okay, but that's the idea there. I'm going to see if I can stop recording. Yep, okay. So let's see how this worked.